With that, let us start talking about scheduling, and this is basically now the next chapter, chapter 7, I believe. And let me just start by saying why is scheduling important in real life, and then we will apply it to our computers. So when you go to a supermarket, which cash register do you go to? You have multiple choices. If you own a large supermarket and have 30 minutes queue at your registers, what do you do? I mean, this is again a very simple scheduling problem. So let us basically apply the 3 points below on if you're the buyer and if you're the supermarket manager. If half of your customers buy less than 10 items, the other half buy more than 50 items. Do you mix them, or do you make some registers that are faster for them, or do you put the people who have 10 items in the front of the queue? I mean, these are all things that you can basically decide on. If 10% of your customers need to go fetch something they forgot on their shopping list, so you're basically going to start scanning their items, but then 10% of them remember that, oh, I totally forgot about buying milk for the children, need to go all the way back to the end of the store, fetch the milk and come back. So if 10% of the customers do that, every one of them takes like 5-10 minutes to get the milk. And because this is the different types of milk, should I get skimmed, should I get full fat? So this will stall everyone. So how do you handle this? These are all examples of why scheduling is important. Operating system scheduling is not different. Your aim is to improve performance, basically improve the response time or delay, which is the user perceived time to do some task. And we can call it also turnaround time. Basically, once I'm in the system, how long does it take me to get out of the system? You want to improve predictability. You want low variance in response times for repeated requests. So you want basically for all similar customers, you want them to be served as fast as possible, but with some predictable time. Because if I'm going into a supermarket thinking that, well, this will take 5 minutes and it takes 50 minutes, I will be pretty unhappy, right? So I want some predictability. You want throughput, so you want to serve as many customers as you can. You want to account for scheduling overhead. You want the clerks, the people, or the people working at the shop to be pretty fast with scanning things. You want fairness. You want no customer to feel that, oh, I've been left out because I bought more stuff and I'm paying this place $50 more than the person who's just going to get a packet of gum, but still they put the guy with a packet of gum because he has a single uh, item in front of me. You do not want starvation. You do not want the people with 200 items, people with very large families buying like 300 items or something, to spend their whole day waiting for everybody to finish and that they can go last. So in essence, you want in an operating system, you want the exact same traits. You want the exact same performance traits. You want response time. You want your applications, your processes to finish as fast as possible. You want the running time for the application to be predictable. Otherwise, you wouldn't even be able to program many of the applications. So most games, for example, depend on the real-time feel of how your video happens with your gameplay. So you want this sort of predictability of how long it takes to actually finish a small task, like rendering, for example, or something like that. You want throughput, so you want as many processes to finish as possible. You want to reduce the scheduling overhead, basically reducing your operating system overhead. You want fairness, so all tasks, all processes should feel equal or should have some notion of equality. You do not want starvation, so applications with high computational demands would wait until the very end before they actually run. And performance is actually equals to money. So a super optimal solution, I have the best optimal solution, but I can get it to you like 10 minutes after 10 minutes. So there's a large scheduling overhead. Might be much worse than even the worst solution that will serve all your customers slash all your processes in 2 minutes. It's still the worst solution from a mathematical optimality point of view because it takes 2 minutes, while my super duper optimal solution that took 10 minutes to compute will reduce the processing time to 10 seconds. But still, I mean, it took me 10 minutes to reach that. So, as I said, these are basically, this is actually a repeated slide with only turnaround time, yeah, as response time. Yeah, I think this is roughly the same slide. It's just, yeah. So what are we going to try to cover? We are going to try to cover scheduling for multiple environments, some queuing theory, some things about overload management, a case study, a look at the scheduling document. This is what we will try to cover over the coming week or so. So the coming 2 videos. Well, not for this week, but for next week. So this is what we're going to cover, because the next video lecture will again be on the Linux kernel for this week. So basically the week after. So the first very simple way of doing scheduling is, and the most basic algorithm one can think of, is the first in, first out, first or first come, first served. Whoever arrives first finishes, I mean, continues getting service until done. So if a process arrives first, it controls the CPU for as long as it needs. FIFO has a number of positive properties. It is very simple. I mean, we're standing in a queue, and that's it, and thus it's very easy to implement. And given some of the assumptions, it should work pretty well. So for example, imagine 3 jobs that arrive in a system, A, B, and C at roughly the same time. So T arrival is equal to 0. FIFO has to put some job first, and let us assume that all of them take 10 seconds. And let us assume that A arrived just a millisecond before B, just a millisecond before C, which arrived just a millisecond before C. So what will be the average turnaround? What is the average time it will take for a job? I mean, you can see that you will schedule A until completion, B until completion, C until completion. Now we're not talking about any timer interrupts or anything. You're just like, will not stop you as long as you're using the processor. A finishes after 10 seconds, B after 20, and C at 30. So the average response time for this application, for this scheduling policy, will be 10 seconds, which is what it took A to finish, plus 20, which is waiting time plus processing time for B, and C, which is 20, and 30 for C, which is 20 seconds or 20 time units of waiting time, and 10 of processing time. And if you sum this, you get an average of 20. So on average, a process will be done, will take 20 time units. So if we relax one of our assumptions, that basically each job runs for the same amount of time, and let us assume that A takes 100 seconds while B and C each run for 10 seconds, arriving in that order, one slightly before the next. So if you assume these 3 jobs, A, B, and C, A runs for 100, B runs for 10, and C runs for 10, arriving in this order, what is the average turnaround time? You should be able to use the exact same logic that we used for the previous equation to calculate the average. Okay, so this is how it would look like. You have 100 milliseconds or 100 seconds for A, 10 for B, and 10 for C. So if you want to calculate the average turnaround time for this application, you have 100 plus, for B it's 110 because it waited for 100 time units, and then 10 for processing, plus 100 plus 120 for C because it waited for 110 and took 10 time units to process. So the average turnaround time is now 110. So this is what is called the convoy effect. where a number of relatively short potential consumers of a resource get queued behind a heavyweight resource consumer. This scheduling scenario might remind you if you have a single line in the grocery store, basically, and someone has like 300 items to scan, and I mean, everybody has been there. So, what can we do to easily fix this? And you have the shortest job first. So, it turns out that a very simple approach to solve this problem is actually shortest job first, where you basically put any job that is faster than the next one to run first. Okay, so in that case, instead of having this time for all three applications, you will just switch. So you'll have B running first, C running second, and then A running for the rest. So now, if you try to calculate the average turnaround time, it would be 10 for B plus 20 for C, because it had to wait for 10 time units and then process for 10, and then 120 for A, because it had to wait for 20 plus 100 time units for processing. So all of a sudden, your average turnaround time is now 50. So you have gone down from a very large average turnaround time to 50, almost 50% faster, and this is quite impressive. So let us assume that the jobs arrive at any time instead of all at once. So assume that A arrives at T0 and needs to run for 100 seconds. B and C arrives at T10 and each needs to run for 10 seconds. What is the average turnaround time with SJF, with the shortest job first? And the answer is 103.33, because now, I mean, you're back to the previous scenario almost. You have to wait for 100 times, for 100 time units to, well, you actually have to wait for 90 time units before B starts processing. And then you add, I mean, this is a very weird way to calculate it, but I think it's the way that, that probably, yeah. I mean, these are slides from the previous book. So B and C arrives at 10 time units. A has already started processing. So since you have no timer exception, timer interrupts, you just B and C have to wait, both of them, until A finishes. So B has to wait for 90 time units before it's, and then it takes 10 time units to process, so it's 100. It takes 100 100 time units, and C has to wait now for 100 time units, basically 90 until A finishes, 10 until B finishes, and then run for 10. So the average is 103.33. So the shortest job first problem is that, as you can see, even though B and C arrived shortly after A, they still are forced to wait until A has completed, and thus suffer the same convoy problem that we tried to solve. So with this, I'm actually going to stop talking about scheduling. I'm going to give you some random stuff that is going to be useful for your assignments and for your life in general. We'll continue with the scheduling part in the next, well, not the next video. Again, the next video will be more on Linux. The video after that will be more on scheduling. So some random stuff. First of all, debugging is what you're going to be mostly doing in software development when you're in industries. So you spend 50% of your time doing debugging. For kernel development, that is even a longer period of time. It actually takes a lot to change a single line of kernel code. If you go through the Linux kernel, you'll find a lot of comments that basically says, well, please do not touch this number. We have tried with all other numbers we could think of, and we couldn't find a good number. So, and this is the only one that worked. Please keep it like that. And they do not even have an intuition on why it worked. They just tried it, keep trying, debugging, and until they just like, okay, this is a number that works. Let's stick with that. There are many comments like this. We'll actually go through them. You'll find also lots of profanities in the comments. You can actually search grep the whole kernel code on GitHub, and there are many profanities because people get pretty. Some of them are basically because people describe others as with profanities, and the others are more like, okay, we have tried every single thing. We're so insane now. We are very, very upset. So we just have added this comment to tell people, please do not touch this number. So what you want is you want to reduce the time you spend in debugging and produce the working code with the smallest effort. So you should optimize the process that involves you, the code, and the computer. And to do that, please do not start coding before you understand the problem. Do not think that while I'm coding, I will understand the problem better, but rather the opposite. While coding, you will get so lost in the details that you might actually branch into something that completely doesn't make any sense. So you need to understand, then design, then code, not the opposite, not start coding and then, oh, this didn't work, let me try the other approach. You try to form hypotheses explaining the bugs that you find. So yesterday I was talking to one of our grad students, and he was describing a problem that he was having. I basically made the very quick hypothesis: are you basically using floats instead of ints? Because in Python, that's a big thing. If you use ints instead of floats, and since it's weakly typed, you do not really specify the different types when you define a variable. That basically means that if you this might make you produce the wrong result. So I mean, we made a hypothesis that, well, you probably used ints instead of floats, and you go from this, and he debugs from that, and he basically gets finds that as an issue. So you make a hypothesis: why can this happen? And typically you make your hypothesis will be based on how proficient or how much you know the language. I mean, many of these small mistakes you will make, and you start ruling out things. So now I have used the correct types, I have used the correct calls, I have used the correct numbers, I've used the correct arguments, and most of the bugs that we write are actually logical bugs that are stupid. Always walk through your code line by line. Debuggers are there for a reason. While the kernel does not have a debugger, but most other programs do have debuggers. You can debug using Eclipse or something. Use module tests, basically trying to make sure that each part of the code works, and develop code in stages. If you write 100 lines of code and find that, well, the output does not conform to what I expected, it's much easier than if you write 3,000 lines of code distributed across 10 classes and then basically start trying to find your way out. Well, it doesn't work that way. So next time we'll talk more about CPU scheduling. We will probably next time, as next week, we'll talk more about the CPU scheduling. Actually, the next lecture, which I'm going to record today, also I'm going to, as I said, to try to record all lectures starting from now in the beginning of the week for the whole week, so that you guys have enough time to watch it and so on. So the next lecture will actually be on the Linux code. We'll go more into the Linux code. I hope this lecture was less boring than the previous one, and looking forward to meet you on Thursdays.